All right, it is. It's now 3 minutes after, and it's this time to start the second half of Jürgen's presentation. I'm sure you all remember the title from the first time, so
Yes, yes.
it
Let's
will
all.
it
I
will
mean,
probably it will probably appear on the screen in a second, and so
yeah.
please give the screen and
Uh,
Jürgen your undivided attention.
yes, exactly. I'm counting on all of this being completely fresh in your minds, of course, from a week ago. So let's see if I remember the title. Okay, so I said the title was originally Quot, where we've decided to downgrade to a hill. So sheaf counting invariance on hill then C4, and this is still. It's good to remind you, this is still joined with Martin Cool. Right. Okay. So where did we get to? Where did we get to last time? Well, we started out with. So I started out explaining the K-theoretic DT invariance on C3, and we upgraded to looking at C4, which is what we're actually interested in, and we have now here a torus T, which is three-dimensional, and it's a subtorus of standard four-dimensional torus acting on this thing. So it's the Calabi-Yau torus, the thing that makes this act in a Calabi-Yau fashion. Right, and we had the geometric moduli spaces that we're interested in. The moduli spaces of the sheaves, which we want to count, are the Mn and Hilbert schemes of endpoints on C4, and we want to compute the certain Euler characteristics or integrals of certain K-theory classes. So let me just write down what these were. So we wanted to compute this twisted virtual structure sheaf tensor with the following class. Some tensor with some other class. So just to remind you of the notation, by this thing I mean the alternating sum of the ith wedge power. If I put a hat on anything, it means I want to symmetrize it, which in this case is saying, well, okay, here I better. So that means tensor with the inverse square root of that alpha, making it more symmetric like, and y here is just some formal parameter. That's the sort of that's the notational problems in that object, in defining that object. So this Euler characteristic here is defined via localization, so it lives. This is some element.
Sorry, what is O n in this
bracket? Good. Let me also specify this thing. On is the tautological bundle. Tautological. So that's the bundle. That's the bundle on the Hilbert scheme, such that the cheap and informal way of defining it is to say that it's fiber at a point Z. So Z, a point in the Hilbert scheme is a subscheme, right, inside of C4, and this thing is the global sections of this subscheme. So some rank, it's a rank, it's some rank n bundle. Right. Okay, and this is defined by localization. So what does that mean? It's going to be the thing we're computing. What is it? Formally, it's an element in the localization of the T equivariant K theory of a point. which means it's a rational function in the coordinates t1, t2, t3. So
since this is a slightly technical point, maybe I should point it out. It's not, you don't need localization to define it, right? I mean, you define it by definition. You just compute, since it's an infinite dimensional space, but it's graded, and so you can you still kind of compute it by.
Right. Right. So I guess you're saying right. Right. So if this were a sheaf, right? If this were a sheaf, say a coherent sheaf, or if you write it as a finite formal difference of coherent sheaves, then yes, I mean, this would be, you could think of this as a power series, right? Some infinite power series giving the character of this.
That's right. So it is a, so in other words, it's that Euler characteristic is some infinite, since an object's not proper, it's an infinite dimensional space, but that infinite dimensional space carries representation of some group. It makes that character is well defined as the same as defined by localization.
Right. Yes. So and then I'm slightly cautious about, I mean, one thing one has to be careful about here is that this object, which we haven't yet defined, right? So we got to last time we got to state a theorem about this thing without actually defining it, is in general, when this is defined in general, it's not necessarily the class of a sheaf. Anyway, but of course, yeah. But usually, I mean, you expect this to be the class of a sheaf, and then yeah, you don't have to define it by a localization. That's true. I'm not sure if that technical point applies to this scenario, but right. So defined either as a rational function or as a power series, giving the character of some infinite dimensional representation. Right. So so as I said, I mean, this guy is well, as the way I phrased it last time is kind of problematic. We didn't really define it, and we gave some we had an ad hoc definition of this. We had an ad hoc definition of, I didn't even define the object, but we had an ad hoc definition where the Euler characteristic of so if you take something like this and you twist it by some sheaf, then I claimed what you should be doing is sum over all the fixed points, and you should be taking the square root of wedge bullet x to OZ dual divide by. So these are now both T representations. So thinking of them as T representations or as Laurent polynomials in the TI, we get. So this was the previous ad hoc definition, which is slightly underspecified because there's a sign choice at each point. So now I want to turn to giving you the actual definition for which this thing becomes a theorem, becomes a localization formula. Okay, so we had so what I mentioned last time was, so we want to use the work of, we want to use the setup of Owen Thomas for defining these this symmetrized virtual structure sheaf. Okay, so let's recall what the standard model for them is. So the standard model is what you expect the moduli space of sheaves on a Clavier fourfold to look like locally, which is you expect, so the modular space, M sits inside some ambient space A, which is smooth. And then on A, there should be a you have an SO to C bundle Q, which we want to think of this. We want to think of this as a vector bundle with a. So we want to think of Q as a vector bundle with a quadratic form. So we have this small q denotes the quadratic form. So this is some non-degenerate. Quadratic form, and this is an SL bundle, so there's an orientation which we'll get back to shortly. Right, and then you also have an isotropic section of Q. Right, so something for which this thing is identically 0, which is what defines M, such that M is the vanishing locus of S. Okay, so once you have this, then you can go to and read Ode Thomas, and you can see what the class is. So I want to give a somewhat different definition from what they do, which works only in sort of more special cases. So where you have even better assumptions than what they need. So here's something which you can hope for in this geometric situation. So you can hope that there exists a maximal isotropic subbundle L inside of Q, right? So maximal isotropic. So by that I mean that the rank of the bundle is exactly half of Q, right? And I mean that the quadratic form identically vanishes on L. Okay, so if you have this, then automatically there's the co-kernel. So then you have a short exact sequence. Well, okay, so you always have a short exact sequence. You have a map of bundles, but the quadratic structure on Q tells you that the co-kernel is isomorphic to L dual, right? So this is something, I mean, so if you work locally, you can always just pick a maximal isotropic subbundle, and I mean, this always exists locally, but for this to exist sort of globally on A, that's a kind of special thing, and you really shouldn't expect that to be true in all cases. And here's an even better, here's an even better thing you can hope for. So the dream case is when actually this short exact sequence splits. So Q is actually isomorphic to L plus L dual. Okay, so this is so in this case we have an SO2N bundle, which is as simple as can be. It's just you take one vector bundle, take its dual, and you take the quadratic form, which is just a pairing of L with its dual. Okay, so
in which category are we now? In the Q was a topological bundle, or it's all algebraic bundle?
algebraic. So
Okay.
I want to say this. So this is an algebraic. So everything here, I mean, I'm sure you could do I'm sure what I say could be also done analytically, but somehow for the example that I want to.
Okay. No, analytic or algebraic, that's the same.
No. Okay. Sorry. Yeah.
Sure.
Sorry. Yeah. I mean, definitely, like, it's important that it's stronger than topologic. Yeah, topological. It's
okay.
Yeah. Right. So all maps here are algebraic or holomorphic or whatever. Yeah. So there's a different take on this story where you really use topology and real bundles, but we'll see that we don't. I mean, we just don't need that side of the story for our purposes. So we can do everything completely algebraically. Okay, so last time I think the last thing I said last time was that the Hilbert schemes that we care about actually globally fit into the standard model of OT, of Owen Thomas. And not only that, I mean, the dream case applies to so Mn, I mean, so this, taking this to be M, this sits inside the ambient space, which is the non-commutative Hilbert scheme, right? So this now plays the role of the ambient space A, and so you can, so the Hilbert scheme is cut out from the non-commutative Hilbert scheme by an isotropic section of an SO2n bundle, and not only that, this bundle actually splits as some bundle plus some dual bundle. So really, if we want to, so the point is that for working on the Hilbert scheme, we really only need to understand what this this virtual structure sheaf looks like in the dream scenario, where it has an extremely explicit description. Okay, so I want to say just one little thing about orientation, which is that, so I've sort of neglected to emphasize this, but I mean, Q isn't just a bundle with quadratic form. There's also, I mean, this is an SO bundle, so there's also an orientation on it, and there are various ways of specifying. I mean, there are various ways of giving the data of that orientation, and for our purposes, the easiest thing to say is orientation. An orientation of Q is determined by saying L is positive or negative. Okay, so this is sort of a matter of so there's a notion. So if I give you an orientation, that means you can give a sign to any maximal. So if I give you an orientation of a quadratic space, that gives a sign to any maximal isotropic subspace. And conversely, if you fix a maximal isotropic subspace and give that thing a sign, that's the same thing as specifying an orientation. So as a matter of just convention, we'll just sort of from now on always pick the orientation. We'll orient Q so that L is positive. And if you were to choose the other orientation, then the virtual class would change by a sign. But this is one choice you make, and going into defining this virtual class, you need to make the decision of how you want to orient your bundle queue. It's part of the data defining the class. Okay. Right. Okay. So now we're in the dream case, and we want to specify what this symmetrized virtual structure sheaf is, right? So so in the dream case, we had our section, some isotropic section of Q, and that's given by, since Q splits, so that's given as SL perp, where SL is a section of L, and SL perp, sorry, SL dual is a section of the dual guy. Right. So now I can write down, I write down a complex on A. So I consider the following set to graded. So it's not a complex in the usual sense. Well, depending what you take to be the usual meaning of a complex, but I think of it as a variant of a complex, where I started by taking the Koszul resolution associated to one of these two sections above. So I take this thing to be let's see, what do I want to think of this as? I want to take this to be the dual of this section SL. And this goes on, so this gives you a Koszul resolution. Well, some Koszul complex at least. Okay, that's something. Then I start adding arrows going the other way, using the other data in my isotropic section. So here I wedge with SL dual and right. So here I have arrows going rightwards, and I have arrows going leftwards, and I declare that the differential here is the sum of these two things. And then if you keep, so the Norwegian expression is if you keep your tongue straight in your mouth and you do this properly, you check that this actually is a complex. So here you get d squared is equals 0. So this is a complex. But it's only, I mean, the differential doesn't increase the degree by 1. It just sort of changes the parity of the degree. So this is a complex which only has a Z mod 2 grading, not the usual Z grading. So so I write down this complex, and I want to take this complex, and I don't quite want to take just this. I want to take I want to twist this. I want to make this symmetric. So I want to take this and twist it by det L, some square root of det L. Okay, so I from the data of this quadratic bundle, assuming you have a splitting and a section, I write down this complex. So this is a complex now complex of sheaves on A. Okay, so then we can check that. Well, one can show that if you take the cohomology of this thing, so this is now just something which is even odd graded. This thing is supported on, supported on M. So you can sort of, I mean, this is some bit of algebra, but you can maybe see that if you're in a point where S doesn't vanish, then either reading this, either sort of just looking at the rightwards arrow or looking at the leftwards arrows, this is the Koszul complex of some section which doesn't vanish, and the Koszul complex of a section where it doesn't vanish is the cohomology is trivial. So that's giving you some indication, at least, of why it's supported on M. But it's actually, I mean, it's actually scheme theoretically supported on M. Okay, so you have this this setmod 2 graded sheaf now, this cohomology sheaf, and then I claim, well, or I don't claim, but it's just a fact that you can take over this symmetrized virtual structure sheaf to be the class of this thing. Inside the K-theory of M. Okay, so that's one way, at least, to define the symmetrized virtual structure sheaf. So okay, so there are many remarks to make about this, but let me just sort of, okay, so if you're only after so for a rough understanding of this, it's useful to look at what happens when you push this back into A. Then you can compute it. Then you can compute it just by using. So it's, I mean, so this is a complex on A. You take the cohomology of it to get something supported on M. But if you push that back into A, you can just use the complex itself to compute the K-theory. So, for instance, the push forward this thing is the symmetrized wedge power of L dual. Okay, so you might ask, why do you bother sort of writing down this complicated complex when the class itself is just the symmetrized wedge power of, the symmetrized wedge power of L dual. And the point is, it's really, I mean, even in this simple case where we have Hilbert sitting inside the non-commutative Hilbert scheme of N, it's really useful to have this to have the class represented as something living on M. And not only that, it's extremely useful to have, we don't just have the K-theory class, we have a sheaf refinement of it, right? So this thing, like the thing that's sort of given to us a priori, is some complex living on A. We can take its cohomology, and then we take its K-theory class, and that's the virtual structure sheaf. But we also want to remember that it comes from an actual sheaf, and we'll use that later on. Okay, so further remarks. This thing is, well, the whole definition, really. It's slightly ambiguous. Well, it's just ambiguous still, because of. So it's ambiguous because I've taken a square root of some line bundle here, right? And I haven't specified to you what the square root is. So in general, I mean, it might be that the square root is unique, but in general, you can't expect that. I mean, line bundles can have multiple different square roots. So there are sort of two sort of solutions to that. So one is to modify the K-theory so that the square root becomes unique. And you do this by if you invert 2, and maybe there's some other formal things you have to do. There's a way of modifying the K-theory so that you end up sort of killing the information that different choices of square roots contain. And for computing things, like for getting numbers out, at least for defining the numbers, this is good enough. And this is, I mean, this approach is what OT take to define their class. Or you have to, and this is what we have to do. You have to live with this and actually choose a square root. And what that means essentially is choosing a square root is really we choose choosing a spin structure on Q. I mean, okay, so yeah. In some settings we do this, in other settings we don't. It's kind of, but this is so to define this, so to really define this as a sheaf, which we want to do at certain points. So to really define this, we need to pick that L. We need to pick the square root of that L as a line bundle, as an actual line bundle, and this is doing this, specifying this square root is essentially the same thing as specifying as lifting. I mean, turning Q, which was an SO bundle, and turning it into a spin bundle.
Jørgen, I'm a bit puzzled here. So in addition to non-uniqueness, there's also existence question. There's also abstraction to having a square root or having a spin structure. Is that obviously vanishing here in this case, or is it?
In our case of the Hilbert scheme, it actually fails. So there isn't.
Okay.
So this thing. Sorry. So let's see. So for the Hilbert scheme case, the square root doesn't exist as a line bundle.
Okay.
Yes.
Okay, I guess you'll explain it.
We will come to that. We will come to that. Yes. I'm not proving theorems about things which don't exist. But yeah, sure. I mean, I guess if possible, you can do this, and we'll see that it will show up again. But somehow in a first go, if you just want to sort of define the numbers, then it's good enough to do this modification of the K-theory, and you only get the K class. That's the right. Okay, so another point to make is that the definition is, I mean, it's not obvious, but it's independent of L. So I gave you we had the dream scenario where we had a maximal maximal isotropic subbundle L in Q, but it doesn't. I mean, it's independent of various choices. One can check this, and it doesn't even need. I mean, it doesn't. So this is. I mean, Owen Thomas work in bigger generality, so it doesn't need L to exist. So there are sort of various ways of showing that. If you have a spin structure, you can write down you can write down explicit. Let me just say this. If Q has a spin structure, then we can write the structure sheaf so these are spinner bundles, and there's some. I mean, okay. So the maps here, are determined by the section S. But anyway, there's some like, the point is there is some sort of way of defining this which doesn't depend on the choice of maximal isotropic Lagrangians. But the fact that we have this description is somehow it's concrete and it's convenient for us. Okay, so this was defining the. So now we're at we've actually defined the thing that's symmetrized virtual structure sheaf. So right. So now we can turn to the next sort of lifting things out of Owen Thomas, which is we can now compute these things using their localization formula. So they give a general localization formula for computing these symmetrized virtual structure sheaves, and for general T action acting on a modular scheme, and it doesn't have to be in the standard model. They do sort of work more globally. But let's stick to our simple example, and let's stick to the one that's relevant for us. So let's assume that the torus acts on everything, and the torus fixed points is something which is 0-dimensional and reduced, so really isolated, scheme theoretically isolated fixed points. And let's say we're still in the dream case. So we have this maximal isotropic L inside of Q. Sorry, so we have, let's do something even better to say we have Q. I mean, all of this can be weakened, but let's just keep it as simple as we can. Okay, so then in that case, what do Owen Thomas? What is the formula reduced to in that case? Well, in that case, they tell you that to compute this thing, what you should do is you should, well, there should be a sum over fixed points, and you should take the symmetrized wedge power of L perp, and you should divide out by the symmetrized wedge power of the sorry. Sorry, I'm right. This looks better, yeah. So they so I had a formula down wrong in my notes. So let me try and give you the right one. So you write down these so at a fixed point you take the so move is the complement to the t fixed part. So general notation, for general notation. So if E is a T rep, then I write E as T fixed part and the moving part. Okay, so with that convention, we take the moving part of this thing and we divide by the moving part of this thing, but then we add on, you modify that by a specific sign. Okay, so if you've seen various localization formulas before, then this bit sort of more or less looks like you're computing the Euler characteristic of this sheaf globally on A, right? And that's almost the formula you get, but the formula is modified by a specific sign. And this sign has, that's the interesting aspect of the formula for me is the fact that you have to put in this sign, and the exponent in the sign is here. This thing is the dimension of the co-kernel of, so you take the T fixed part of the co-kernel of this thing. Okay, so it's so this is okay. So I'm at a fixed point. I'm at a fixed point P. I have my section S, which is what was cutting out M. So this tangent space, taking the differential at its fixed point, this tangent space, this section defines for me an inclusion of this into Q, and then I project that further down to L, and I try and compute the dimension of the T invariant part of the fixed of the co-kernel.
Isn't this? Oh, sorry. Go ahead.
No. Yeah. So I just wanted to say that, in order to understand what the contribution is at a fixed point, you really need some understanding of what the section was. This bare data, K-theoretic data of L dual and the tangent space isn't enough to tell you what the contribution is.
Right, but couldn't one think about it like that? Suppose I look at the fixed part, right, of this abstraction theory. Then by the assumption that your fixed point is zero-dimensional reduced, that has to match up to duals, that has to match the tangent space. And so that means your, the kind of the symmetrized lambda of one has to be plus minus symmetrized lambda of the other, and this is the sign you're computing here.
It's,
well, suppose you had a bigger torus. Suppose you had a bigger torus acting somehow, right? And then you could imagine that the situation is such that in fact everything is moving, right? If everything is moving, is that then this is one, right? That sign, because there's nothing torus fixed.
Let me think a little. Yes, if you're right, so if your torus is, okay, so if your torus is big enough, if you have a big enough torus acting on everything, if your torus is big enough that actually P, so right, so you have, let me see it. So so your P sits inside here, and I want to say there are two things you can do to P. So this is I'm just going to give you sort of my naive and informal understanding of this. But you have, so A is the big thing. Here you have the fixed locus of AT, and here you have M is the is where sort of things are cut down by the section, right? And so I mean, what can happen is that P could have been sort of already fixed as an object in A, right? If this bit wasn't here, then P would already be fixed inside of, no, sorry. What am I?
Yeah, well, suppose the picture is exactly like you wrote down. So it means,
right. Okay, so
the fixed locus is transverse to M.
Yeah.
Right.
Right.
Then my understanding is that sign is 1.
The exponent is 1, right? Or
yeah, that sign that's 0, right? That's not the case.
No, I would say that's exact. Okay, so I don't have this. I mean, my expectation is then you would actually I would say the sign is 1 because this thing is one-dimensional, but I'm not 100% sure on that. I mean, let me not commit to that. But this I mean.
Okay, but my thinking is that suppose if the torus is somehow magically very big enough, then there are no invariants of any kinds in any of the spaces of which where you take the co-kernel. And all of that is just trivial, right?
Yeah.
So the dimension is 0.
Right.
And
but I suppose, yeah.
But then if that means we have some expression of the kind, like some type of torus weight over like lambda of some torus representation over lambda of another torus representation. That representation has to now I guess it can get a sign. So that torus I must substitute to 1, and that 1 is somehow supposed to get me a sign. Well, anyway, sorry. I mean, this discussion is taking too long. But, I think everybody can pursue it in their free time. So
yeah. No, but just okay. So we can. This is interesting, and I'd like to. We can pursue this. I can ask you again after. But so my simple point was just somehow that if P were already isolated inside AT, then that sign would be trivial, right? But it's not necessarily isolated inside AT. It might sort of move as a point inside AT, and then cutting it down by this section is what makes it isolated. And there you have to understand what the section. I mean, there's some data in how you cut it down by the section, and that data is covered in is covered here.
Okay, thanks, Jørgen. That makes sense. Thank you.
Yeah. Right. So you really yeah. So the data of the section is important. Right. Okay, so I don't have much more to say about this localization formula, except we can now we can use it in our concrete case. We have sort of, in the case of the Hilbert scheme, we can take this formula and really analyze it completely. And so for a torus. No, sorry. Let me just give you the simple version of this this formula of this proposition, is that we now want to compute in the Hilbert scheme this virtual structure sheaf. Then we have, I mean, then using that formula, it reduces to exactly what we expected it to from before. This this x2 and this symmetrized x1. So that's not automatically what you're given by Owen Thomas's formula. There's a lot of, if you set this up, there's a lot of cancellation happening here, and then you keep track of you have to keep track of this sign, but all the section S and the bundle Q and everything here is sufficiently explicit that you can, I mean, there's work that goes into this, but you can really, with sort of explicit description. So we have we can compute this as a sum over fixed points, and there's an explicit description of the choice of square root at each point. I mean, if you ask me to, I could write down an explicit character formula for what the contribution is at each fixed point, and I could give you a combinatorial recipe for what sign you need to tack onto that. So this is some messing around with resolutions of x groups and playing with these expressions to find this. As it turns out, actually, this, I mean, for the main theorem, there's sort of, this is, in some sense, this working out the sign is, well, so actually pinning down the sign is explicitly, is logically independent from the other main result we have, which was the formula, right? So so the formula we want, we want to compute the generating function of these things, and for a reason I haven't quite specified, although I've hinted at it, we don't want to just compute the bare virtual structure sheaves. We want to compute the thing where you also tensor with this bundle, this symmetrized wedge power of the tautological bundle. And the formula we're after here is the platistic exponential of something. And I mean, to a first order approximation, the important thing is that it's a simple function, and it's a rational function. So here, just to remind you of the notation, this thing means alpha squared root minus alpha minus 1 over alpha, and this thing, so if you have some function of the zi, this platistic exponential is the ordinary exponential of the sum of the following form. Okay, so here you have a rational function, and so here you have a rational function, and you apply this formal operation to it, and this formal operation is meant to capture taking the infinite symmetric product of some representation of vector space. Okay, so the shape of this formula, and of course the fact, I mean, the shape of this formula is very similar to what we had in the three-dimensional case, and in the three-dimensional case, well, the sort of key concept that explains the shape of this formula is the notion of a factorizable sequence. So taken from the proof of that thing, taken from the proof of the computation of the DT3 invariants. Right. Okay. So so let me try and just briefly say how I think of this. So the general problem being to compute Euler characteristics of sheaves Fi. So here Fi are sheaves on sim I X for some scheme So this is something, I mean, so there are various natural candidates for what Fi can be, and that gives you lots of different enumerative geometry problems. So that would, and in our case, it will be the Fi will be these guys. And the so the thing that often happens is that often Fi is sort of defined locally, meaning which means that if you have P1 up to Pi and Q1 up to QL with P's distinct from Q's, then what the sheaf looks like, so what the sheaf Fi plus J looks like at the point Pi and sorry, P, let's do L. What the sheaf looks like at this point in the symmetric product, which is the union of these two other points, is determined by, well, let's just skip to the concrete case. So not only determined by, but it's actually isomorphic to the tensor product of the two it's actually given as a tensor product of the fibers of the sheaves on evaluated on the P's and the other sheaf evaluated on the Q's. So this is, I'm messing up my indices here, sorry. So there's I and there's J. And the claim is, so the criterion we want on our sequence of sheaves Fi is that evaluating it at some point which is of this form, well, you should be able to do that by evaluating Fi on the first group of points and tensioning with that with the evaluation of Fj on the second group of points. So that's the sort of rough idea. Well, that's half the rough idea of factorizability. So what that means informally is that if you can say this, then away from the locus, there's this small diagonal inside of sim nx, and if you're at a point where, if you're not in such a point where you know in the symmetric product where the point is just n copies of the same point, then you can split it up into two groups, and essentially then Fn is determined by fi for I less than n. I'm being extremely informal here, but okay. So once you have this property, you should be able to say this puts constraints on these things because essentially this the thing you care about. Suppose I know what these guys are all the way up to n, right? Suppose I know how to evaluate all of these up to n, and fn I can say, well, on a huge chunk of this symmetric product, I know what it is. I might have to sort of modify it along this small diagonal, but that's a very, very sort of restricted kind of modification compared to sort of the just not knowing what it is. So basically, the idea is that having this relationship puts very strong constraints on the fn and on the corresponding evaluation of these integrals. So let me give you the so there are various ways to phrase the definition, and let me just give you the one which is adapted to our case. So the definition of factorizable is well, it's a factorizable sequence if we have the following data. So first of all, let just p ij from, so there's natural addition map which we've been using already. Right, we have this addition map of just adding points. Okay, so we specify. So specify for I and j, we specify an isomorphism fi box product fj to the pullback of this thing, but we only specify this on the open set where consisting of these, of this, sorry, on the open set where you have this condition of non-colliding p's and q's. So p's and q's distinct. Okay, so this is saying, this is just a family version of this property that we had upstairs here. This is just saying, at each point we should be able to decompose this thing into this thing. Okay, so this satisfies conditions. So we must have that the two compositions. So there are now two natural compositions, fi, fj, fk should be isomorphic to p, and let me just leave implicit what this pullback map is. So there are the two compositions here, and they should agree up to scaling. And that's in practice usually easy to get. And then we have the SN equivariance, which is saying that fi, the isomorphism here, this thing should agree with, so you should be able to swap I and j. Okay, so to be precise, I should write down a specific commutative diagram here and be technical, but the point is somehow that well, informally you should be able to reorder these and that shouldn't really change the isomorphism. And that thing, I mean, that thing in practice, in our case, is the thing that's really it's really hard. So getting this property to hold up to sign is kind of easy, and then getting this to hold, showing that you can swap factors and not change anything at all, is kind of that's what's been causing us a lot of grief. But in any case, those are the things you check to generate a factorizable sequence, and then what Andre calls a lemma, I think. It's a very useful lemma, is that if you have this, so if Fn is a factorizable sequence, then there exists sheaves Gn on X such that the generating function of, so evaluating all of these Fn, you can really express this in terms of something far simpler here, and the far simpler thing is the Euler characteristic of these Gn. So, and this is really simpler. I mean, these Fn are kind of, relatively complicated because they live on these singular spaces, and we don't really have any. So the symmetric products in general will be singular, and they might be, for various reasons, hard to deal with. These sheaves are well, this is a very much simpler set of data living on a smooth. Well, I always assumed that X was smooth, so this is I meant to assume that X was smooth, so this is a very sort of very much simpler set of data. And so the fact that the formula we're trying to prove has a platistic exponential in it is sort of good indication that this has a chance of being factorizable. And so in some sense, the most technical part of what we do is verifying this. Well, maybe it's more than a lemma here, but we show that the sequence this thing tensor with the insertion so this doesn't really make sense. So this is a K-theory class. It doesn't make sense to call this factorizable, or depending on your definitions at least. So so what I really mean is I really want to take the push forward of its sheaf refinement to sim NC4 is factorizable. Okay,
yeah, maybe I should point out here that that's really important here. So the way it's written in my notes, it's pretty careless, because I don't stress the importance that you need to have that sheaf refinement to talk about factorization, and that's we should all follow the treatment that the subject received at the hands of Martin and Jørgen. So this is. So in particular, what Jørgen's playing today is also applicable. More or less, I mean, it's also applicable in the exact, well, simpler, but the exact same thing to the Hilbert scheme of points in C3, and that's there it refines not just in fact the kind of two periodic complex, but the actual complex. And that actual complex is factorizing. But anyway, you have to have that refinement to talk about to talk mathematically about factorization. So
right.
I want to.
And it's also, I suppose, it's also it also applies in interesting ways to the two-dimensional case for certain sheaves, I guess.
Right. There's also two-dimensional version. Yeah, that's true.
Yeah. So this, I mean, it reminds me of things that show up in the Goethe conjecture, where one doesn't really do K-theory classes there, but that's. So I just want to. I'm just drawing a diagram here now, just to. I mean, I'm not going to say anything about how we prove this, but just to have clear in our minds what we need to check here is we have. So I gave you a long while ago. I gave you this thing. And I wrote down this two-periodic complex defined by an explicit resolution. So I have so it's a cohomology of some explicit two-periodic complex. So what we're doing is we have an explicit complex here whose cohomology is supported here, and the same thing upstairs. And we need to compare these two things and check that the sheaf here agrees with the sheaf here. And then we need to check compatibility, and then we need, so the compatibility under composition, and we need to check that things, when you flip I and J, that you actually get, well, the sort of correct SN action involved. And this is kind of a pain once you have to involve square roots of things and check how, like, well, how does the natural SN action induce an action on square roots? And it's yeah. I don't know. It's something, I'm not sure a computer would find it difficult, but the human mind isn't really equipped to think about that many signs at once. That's my feeling anyway. But yes, this is where I should follow up on the previous comment of Andre's previous comment about this. This thing doesn't really have a. I mean, this thing isn't refined to a sheaf, and this is also where I thank Noah to sort of do which he pointed out that factorizability shouldn't work for this. So the whole, I sort of, it's late in the game to tell you this, but the reason why we need, well, at least from our perspective, the reason why we need to keep this insertion in the picture is that without it, if you're just considering this bare virtual structure sheaf, then it wouldn't be factorizable, and the explanation for that is it doesn't actually even refine to a sheaf. So in order to play this factorizability game, to apply this this lemma, or to just have something fit in the definition, you really need to be a sheaf, and the thing that you can check is a sheaf is this thing. So basically, this thing by itself doesn't exist because there's a certain square root you need to take, which doesn't exist. This thing by itself also doesn't exist because in the definition of this symmetrized guy, there's a square root which doesn't exist. But you know, these two square roots that don't exist sort of cancel out, and so this thing actually admits a sheaf refinement, which is what we can play that, which is what we can show is factorizable. So that's the right. So that's one reason why you need to have, you don't really want to compute these things. You want to compute the full thing with insertion, or at least if you want to have something which is nice in terms of the logistic exponential. Okay, so now, okay, so we now know that this is factorizable. Okay, now we can apply this. The main sort of numerical output of this is we can write down.
Sorry, Jürgen, can I just maybe clarify the point you just made?
Yes,
this is somehow before any factorizability. You're saying that something like the virtual whatever canonical bundle is like the determinant of the tautological bundle, something like that, right? So
yes, exactly.
So if you'd like to extract the square root of 1, you have to hit it with something that had that determinant so that the overall square root exists, right?
Yeah, that's exactly it. Right.
Okay.
Right. Although, yes, yeah. It's not clear that it's the virtual canonical bundle, but whatever, some square root appearing in the definition.
Right, I understand. I mean, it means there's some analog of whatever.
Yeah.
Some determinant that is not
exactly.
square.
Yes, the determinant of this L that we had a while back it fails to have a square root in precisely the same way that this thing fails to have a square root. The determinant of this thing fails to have a square root.
Okay.
Yeah. Okay, right. So now we can apply. So a corollary to factorizability now is the following numerical statement, which is that. So recall now. Okay, let's stick to the thing we want to compute is this fn. So we have which is factorizable. So we now have that. This thing has a particularly nice form in terms of just sort of numerical, right, expressing this in terms of numerical functions. So let's see, sorry, I should be summing and I should be so summing over n. Sorry about this. So it has this form where crucially, this is where you get a huge constraint, is that this thing Gn is a Laurent polynomial in the TI, and perhaps we probably want to take some square roots here, but that's secondary. Right. So so this is I mean, from before we basically knew nothing about this. Now we know that it has a very, so it's saying that this, I mean, I just want to say this is an extremely strong constraint on this generating function that we care about. And the proof, let me just give you one proof today, is that if Gn is a sheaf on C4, then the Euler characteristic that thing is a Laurent polynomial. The character of this thing by localization or otherwise, you check that this thing is exactly a Laurent polynomial with denominator exactly what we had before. So taking this thing and putting x equals C4 precisely means that that the generating function we care about is a Platystic exponential with this particular shape. Okay, so now we got this formula is sort of on the back foot. We're really now we're sort of now the rest of the proof is kind of just looking at Andre's proof in the 3D case and carrying out the steps, which are I wouldn't call them formal, but there's sort of now we're down to manipulating polynomials and these localization contributions. So let me maybe just okay. Let me just quickly sketch what goes into the to proving this now, and then that's what I have to say. So so to prove the formula, we need to show so that this this thing is equal to, so we had a specific formula we wanted to check, and well and the proof has a sort of I don't know, it has a nice kind of by steps feel to it, in that you sort of you chop it up, you chop up the formula in pieces, and each of them sort of falls one by one here. So previously we dealt with this factor sort of fell to factorization. We can now treat this factor, so we can so one shows that all Gn are divisible by exactly this factor, and that's that you get out from looking at the localization contributions and looking at the explicit contribution from each fixed point. So basically you check that this actually is also already true at the level of each fixed point. So okay, so that leaves us with so that leaves us now with sorry, the next yeah. So taking the limit as t goes to infinity or 0, one can.
Jürgen, can you make an argument of the kind that I'm always have, since I have something zero-dimensional, right? It's never fixed under translation, right? So I always have T1, T2, and T3 in my tangent space, right? And so from x1, I have a multiplication to x2, and that can you make an argument that always the products of two things always actual, like actual elements and non-zero elements in x2?
Sorry, I didn't follow that question. Sorry. Could you say that again?
So if I have like T1 plus T2 plus T3 plus T4 is always a part of my x1. Because I have something zero dimensional.
You can always translate.
I can always translate it. It's never fixed, right?
Yeah. Mm-hmm.
And so then from x1, I have a wedge product to x. I have a product to x2.
Yeah.
So if I take the products of these elements, I should get some elements in x2 of weights precisely ti times tj.
Right.
And is there some abstract argument they're always non-zero? Because that will prove that all these things divisible by.
Well,
I'm sure you make an argument which is
no, yeah, for sure. I mean, the argument is a variation on the argument you make. I don't. Let's see why. I mean, I guess the best answer I can give you now is maybe that
All right.
Well, no,
I don't want to
don't know.
steal the few. I mean, whatever.
I mean, the precious few lines I have left. No,
yeah,
no, yeah.
you don't be sorry. Speaking about pressure and pressures, don't be pressed for time. Just say whatever you want to say, and
Yeah.
We'll be patiently listening.
Okay, yes. Yeah, you can be patiently listening or not. It's up to you. I can give you the few steps remaining in the proof. Yeah. So taking the limit as ti. So keeping some ti's fixed and taking one of them to infinity or 0. So we find in these limits that hn, which is now, okay, so we have now, we introduce hn, which is, you sort of remove the thing which you can remove. So we find this is bounded in that limit. Right, and again, this is sort of this comes out of looking at contributions at each fixed point and sort of basically just analyzing. So the way we can compute the contributions to the fixed point is sort of amenable to exactly understanding how that limit works. Right, but now, I mean, what we proved before, so the fact that they're divisible, I mean, means that the hn are Laurent polynomials in these ti square roots and the y square root. But, and this is the rigidity, is if you have a Laurent polynomial which vanishes in limit to infinity and to 0, that means actually hn is independent of the ti. So really hn is now just a polynomial in y. Okay, so what summing up all the steps so where are we at now with all the steps we have we've done? We now have that the thing we wanted to compute, this generating function, is a platistic exponential, where we now have we've proven that the exponent has almost we almost know it has the shape we want it to have, except we have some mysterious, some yet to be determined hn y. Sorry. So somewhere n, and we have some yet to be determined Laurent polynomial hn y qn. Okay, but now the final trick, which sort of makes this sort of, we were surprised that it turned out to be this simple, as if we now set y equal to t4, then the left-hand side, one can check, reduces. I mean, if we set y equal to t4, then the left-hand side equals the dt3 series computed. So the thing that was that we had discussed in the previous lecture, and that implies that, I mean, let me say what I want to say. This determines hn. So we have a Laurent polynomial. We know what it is when we insert when we change the name of y to t4, and just formally, if we know what it is when we set y equals t4, then actually it turns out we know what it is when y is equal to y. It's a kind of a it's a kind of a funny move, but it works because we know that Hn is a Laurent polynomial, and so yeah, and that's good enough to sort of to prove the formula that we wanted, which I won't. I mean, you've seen it many times already, but this is that's the theorem. So yeah, 3 minutes over. Started 3 minutes.
Yeah. No. I mean, you started 3 minutes late. It's like like a it's actually like a soccer game. I mean,
injury time.
No extra time required. Yeah.
yeah.
All right. In the extra time, we can all ask questions.
Yes.
I can ask the usual question,
Okay.
which is it's not a bad idea to keep asking eternal questions. I think it's already asked in Nikita's paper. So you look at the formula; it has 6 things in denominator, right? So you'd imagine that T1, T2, T3, T4, as well as like what the square root of y times q and square root of y is over q, right? They should be considered as some coordinates in some 6-dimensional space, and with something happening. So have you ever, or have you or anybody else thought about what that 6-dimensional space might be? Or
I can only say, I mean, I'm sure someone has, but I'm also sure that I have. I mean, yeah, I know. For me, it was kind of a stretch going up from 3 to 4. So I've no.
No, but in 3 dimensions, this is then you get 5 things in denominator, and there is a 5-dimensional space. And there's Nekrasov's original conjecture was motivated by some 5-dimensional, well, 5 complex 10 real dimensional computation that matches that formula.
Mm-hmm.
And now we have 6 things in denominator, and
Mm-hmm.
then and one should be wondering what should be another interpretation of that same formula. It has to do with something.
Right. Yeah, that's good. I mean, I'm yeah, that sounds I don't have anything meaningful to say to that other than it would be cool if there was such a thing. Yeah.
Other questions?
So does this sign that's assigned to a 4D partition show up in this argument you outlined here at the end?
Right. So in the so you're asking about the localization formula and the fact that we sort of pin down the sign. Yeah. No. So I mean it does. I mean we don't need to know it explicitly.
Okay.
Right. So but the whole argument somehow relies on the fact that there is a sign, which means so the whole argument relies on the fact, I mean, there's this interplay that there is a global geometric object which is computed by a localization. So we need to know, I mean, that the localization formula works, and then we don't actually need in these like 5 steps here, we don't actually need to know at each given point what the sign is. But what would happen was if you sort of flipped one of the signs, then factorizability would break. So the thing we need about I guess the main thing we need about the signs is we need to know there exists a sign choice such that it comes from something geometric, which means that we can show factorizability. I'm not sure I'm answering your question. This is just sort of my my thought.
Yeah, it's strange, right? Because like some of the sign doesn't, I guess, show up in the construction of the sheaves themselves, but
right. So this.
No, but you can think about it like this. So what does it mean that something comes from geometric object? Like if you have a curve in Hilp C4 which connects the 2 points, and then the sign has to agree on the two sides, and that will lead to some. I mean, the fact that it's going to be Platistic exponential of something relatively simple means that a lot of denominators which are present in the localization formula have to cancel about after a certain computation, and the way this cancels geometrically, has to do with the fact that two ends of a P1 somehow contribute in a certain way that won't cancel each other, and so the signs need to know, having a global geometric object and having the right signs, and in the fact that you can in fact cancel all the poles you have by taking the Platistic, better to say, you take Platistic log of your expression, and a lot of poles in that Platistic log have to cancel, and that has to do with the correct choice of, that fixes the correct choice of sign.
Right. Yeah. I should also maybe mention like that there is an actual also in something I hadn't mentioned. There is also a choice of sign. I mean, we need to orient the theory for each n. There's a global choice of orientation of the Q for each n. And there's, this is in some sense simple, but you need, this is. I didn't specify that, but you need to specify that correctly, otherwise things break. But anyway, that's a separate issue. But yeah, we can determine what the sign is at each fixed point, but in the actually proving the formula, we only need the only aspect of that determination we need is that it comes from something geometric, which means we can make this cancellation happen, which means we can make factorizability hold.
You think so? Suppose you have some general, some more general moduli of sheaf on Calabi-Yau 4. You think there'll be exactly the parallel story that you'll need to hit it with some tautological bundle to have the corresponding X bundle have the spin structure? Is that the computation that can be done somehow abstractly?
I haven't thought about that. I'm not. Yeah, the honest answer is I'm not sure, but that seems like a likely guess, I guess. I don't really understand this conceptually at all. Why this sort of symmetrized virtual structure sheaf doesn't really exist even on C4. It's kind of but right. I guess. There's only. So locally on C4, there's only so much that can go wrong, right? So there's only a line bundle like the Picard group of. Or no, sorry. There's
pick killed C4. Who knows what that is? Yeah.
No. Sorry, but this is. I guess okay. You could be optimistic. So this already failed for Hild 2, right? And there's only so much that can go wrong.
Right.
And so you could hope that somehow, if you can find the thing that works for Hild 2 on a compact, then that would be also good enough. And then I guess it looks kind of reasonable that. Well, if you can sort out Hild 1, like maybe you require. Well, it's a Calabi-Yau, so it is already spin, I guess. So if you can sort out Hild 2, you could hope that it also works in higher.
Right. So I guess what you're saying is that proving such a formula may be a separate issue, but at least constraining it to, if there is some answer, maybe constraining it to by looking at things which is, having things of small, having a particular loci of your sheaves, which things look very simply, then already that would be, that should be enough constraint.
Yeah. Yeah, in general, I don't really understand either in general how this if this sort of formally connects to any statements about the compact case. Like there are lots of ways of doing that in the threefold case, where like the compact computation is reduced to toric cases, but I don't know what one should expect in this fourfold case of if one can actually sort of reduce to C4 or into toric computations more generally.
Okay, more questions?
Yeah, so this L in this case of C4 is just given by picking like half the 6 equations that these 4 matrices commute.
Right. Yes. So we had so Q was a so in this case we had rank Q was 6 n squared, and this is, so it's really it's a wedge to C3 tensor in terms of the non-commutative Hilbert scheme.
Yeah,
it's this thing, and right. So and what you do is you pick no, sorry, it should C4, of course. C4, and so to pick L, you can do various things, but one thing you can do is to take wedge to C3. Just pick three of these equations. So if this is Q, you can take this to be L, where this thing is. Just pick 3 of the coordinate axes, the t-fixed axis. So I suppose I just want to like there's only so much you can do. Like you look at what you want to do is you want to pick a 3-dimensional subspace of this thing which is fixed under the torus action, and that gives you 6 choose 3 possibilities.
It's like in the threefold case.
Well, it has to also be that every weight has to appear. The ways they are paired in pairs, and you have to pick one from each pair, right? It's not right.
Is that right?
Otherwise, it wouldn't be the dual of. It has to be such that your subspace is.
Oh yeah, sorry. It has to be isotropic. That's the sorry.
Exactly.
No. Yeah, you're absolutely right. So okay, so you actually have 8. Okay, let me revise that. You have 2 to the power of 3. You have 8. Sorry. Yeah, but okay. Right. So so the L you choose is either of this form or it's of the dual of that, which looks slightly different. But anyway. Sorry, did you have a second question?
Yeah, so it's kind of in the threefold case, you have to be a little bit clever, right? You write down the superpotential and you see that its critical locus is cut out by the exact equations that you want. But here in the fourfold case, you just kind of like take the equations, and that gives you the
right.
Is there some kind of structure living over these equations that one can expect from which you extract these equations, or like, I guess more generally, is there some kind of 4D version of the 3D model that's a quiver with superpotential? Or is it just like some quiver and I have some edges in a pairing and you kind of mimic this story in that language?
So I don't, so so I came at this from looking at just like looking at the C3 case and trying to do like the same thing one dimension up of like, okay, trying to find an O-Thomas standard model for Hilbert C4. But there might be, it would be natural to in the 3D case, you can write down arbitrary quivers and put a potential on them. And well, there's some conditions for that to be interesting, but that would give you critical loci. And you probably could do some sort of non-commutative 4D theory as well. But I just don't know what examples exist out there. I do know that there's there's a way in which this description here of like getting a description of C4, there's a sort of you can think of that as an operation where you take the quiver that gives you C3 and you do something to it. You add on a trivial direction. And this operation generalizes. So if you have a quiver, like giving you a 3D theory, you can write down a new quiver, which would be sort of adding on a trivial direction to it. And you write down a sort of, well, you get the same thing, a quadratic bundle with section and all that sort of thing. So, you know, non-commutative 3D theory plus times C, that I know you can get in this way, but what other examples exist out there, I don't really know. Was that roughly the question?
Yeah, I mean, it was a vague question. So
yeah. No, so basically, I mean, yeah, I have this example. I don't know what one should expect the general landscape to look like. Yeah.
All right, more questions? Well, if there's no more question, let's clap our hands and thank Jørgen for a wonderful pair of talks, and I'll see everybody next week.
Okay, I'll send you the notes, I guess.
Yeah, please do. Yeah.
Yeah.
Thanks.
And yeah. See you all at some point.